Hello, welcome back as we continue to discuss the wonders of mixed models. Just to remind ourselves where we're at, um, we decided that we were going to put structure into our error term. So in this case here, we have this object called yields. Where is it? Yields. And we're interested in knowing whether or not irrigation, density, or fertilizer plays any role in the amount of yields that we're getting. And we replicated this experiment 4 different times, essentially. We did it across 4 different fields, so these are 4 different blocks. And what we did is we set up a model where we had, right here, where we allowed the intercept, the baseline, essentially, for each field to be different. And so, again, what we're doing is we're adding structure to our error term, because even though historically we've always thought about the error as being that part that we either don't care about or that part that we can't explain, it turns out we can explain maybe a little bit of that variation by allowing each field to be different, to add structure to that error term. And we did that here by saying we would like each field to have its own intercept. And then we could compare that against a model where we don't include irrigation. So I'm going to call that mod null. So now I have 2 different models. There's one that has a slope estimate for the effect of irrigation right here. And whereas our mod null, all we've done here is we have added structure to the error term, but we haven't put any fixed effects in the model to do the hypothesis testing on. And then if we recall, there's 3 different ways in which we can do the hypothesis testing, or at least 3 different ways that we talked about last time. One is to use the lowercase ANOVA function that is part of the base R package. If we were to give that 2 models, here I'm giving it our null model and our full model. If we were to give it that, it would do a likelihood ratio test for us. And what that's telling us is that the full model, or just our model in this case, is the superior model. That is a way to say that irrigation is significant. It's important and it's appropriate for us to model our data using irrigation as an effect. If if we were to use the capital A ANOVA function from the CAR package, it does something very similar. The one advantage of the capital A ANOVA function over the lowercase ANOVA function is that you don't have to include the reduced model. It'll do that for you automatically. And then finally, the last way is if we had loaded in the Elmer test package and we used the lowercase ANOVA function, it's no longer the lowercase ANOVA function that we're used to. R will recognize it as being something that we want to do the ANOVA using the Elmer test ANOVA function, and it does more of a traditional method of doing the hypothesis testing, where here again we're gonna reject the null hypothesis that there's no effect of irrigation and accept the alternative that there is some effect of irrigation. And so that's where we ended up last time. And again, all we're doing is we're adding structure to the error term. And so if we were to look at the summary of our model, the parameters are familiar. How we would go about interpreting them is familiar. It's similar to a normal or a fixed effect ANOVA. Again, in the random effects portion here, that's where we've added some structure to the error term. And in fact, we could say, well, given all of that error, how much of that residual variation is actually explained by fields as opposed to still unable to be explained. And we could do that by just taking these variance components and say 270.4 divided by 228.1 plus like so. Go ahead and do that. So basically we're, of all of that error variation that we had, by putting that random intercept term in there, we're explaining 54% of the variation that before we would have just dumped into the error term, which obviously then is going to increase our statistical power when we do the hypothesis testing, because now the denominator term is it'll end up being a smaller number because there's less unexplained variation in our model. And just as a picture of what we're doing, we can look at the coefficients from that model first. Let's go ahead and do that. I will do that right now. Yes, I will. Coefficients of the model. Okay, so this is the different intercepts that each of the fields had. So each field is receiving its own intercept. Notice that they all have the same slope. So they all have the same effect of being irrigated. It's just starting at a different baseline. And so now, as a picture to see what we're doing, it looks something like this, right? And so here again is our dummy coding about being not irrigated or being irrigated. And then each of these lines here indicates the effect of each different field. And so this is the first field here, the red one. That would be field A, which was overall just had lower yields. And so we've removed that. Okay, and so there's we can add, or we could test the model where perhaps we even add more terms into the error structure to even try to do a better job at describing the error structure. And we can do that by allowing not only each field to have its own intercept, but also allowing each field to have its own slope. And so I can go ahead and I can cut and paste because that's a lot faster than me typing. Okay, and so now I'm saying I want yield to be some function of irrigation, but now I have in front of that pipe symbol right here, I've put irrigation. So what that's telling Elmer is that I would like each field to have its own intercept, but I also am willing to allow each field to have its own slope. So the overall, the amount of effect that irrigation has. And so if I go ahead and I run that, let me open up this window a little bit here. I go ahead and I run that, and let me do it again because I'm getting that normal annoying error here. But notice that I get a warning message that says boundary singular fit. And what that means, well, the first thing that means is that if you get that singular fit, that means that you are providing an overly complex model. Meaning that we're trying to basically do too much given the data that we have at hand. So we're trying to put too much structure into the error term. And if we look at that model, and it's just a warning, it's not an error, so it's not necessarily wrong, it's just probably not the best solution. And if we were to look at the summary of that mod 2, notice that up here where the random effects are, we have, of course, for each field we have an intercept, and then we also have now each has its own slope. But notice that the correlation between the intercept and the slope is 1. And what that means is that R settled on a solution where it basically simultaneously estimated both the slope and the intercept, and they were perfectly correlated. So there was not a unique solution for the slope and the intercept. And again, that singularity warning is telling us that we've pretty much over-parameterized what we're trying to do with the error structure. There's no reason to have a separate parameter for the slope or the error slope for the effective irrigation as well as a different intercept if the solution for them is perfectly correlated with one another. And if we were to look at the coefficients for that model, coef mod 2, okay, notice now that each field does indeed have its own slope, but what I've done is if I put those numbers into a vector, so here I'm going to see how well the intercept is correlated with the slopes by just using our old friend, the core function. Here, indeed, the correlation is 1. And so it's basically they're not able to be independently estimated, and again that's telling us that we probably don't want that in there. But we could look and see what this looks like again. So that's when it looked like when we just had a random intercept model, but we didn't have a random slope model. And I can go ahead, and that's what it looks like when I allow the slopes to vary. So you can see that the slopes are slightly different. It looks like, you know, the effect is slightly different in field A compared to how it is in slope B. But again, they're perfectly correlated with one another, so there's probably no reason to retain that in our model. We could similarly use a built-in function that is part of the Elmer test, which overwrote the older one, which is the step function. And we can use the step function just like we've used step functions before to assist us in model selection. And so I'll go ahead and I'll say step mod 2, and I go ahead and I run that. And let me open this up so we can see it a little bit better. Okay. So first thing it's doing is it's settling on what the appropriate error structure should be, and then it's dealing with what the appropriate fixed effects should be, and it's settling on this model, which is the same model that we were playing with before. What the step function will do, the Elmer test step function will do, is it'll do things in that order. And that being, first figure out the simplest error structure where you can uniquely identify or uniquely estimate all the parameters of your error structure. And then once you have your error structure figured out, then it goes ahead and it works on figuring out what fixed effects should be in there. Okay, good. So let's go back and look at our data that we're playing with here, actually. So here's yields, and remind ourselves that we had more than just irrigation that could potentially be in the model. We also manipulated density, and we also manipulated fertilizer. So those are all other fixed effects that, since we did the experiment, we probably would want to do we would want to probably include in the model to do the hypothesis testing on. And so what I can start with is I can start with a big giant super fat model. And by a big giant super fat model, what do I mean? Well, I'll cut and paste it and I'll show you what I mean. There we have it. So now here's our really big fat super fat model. So yield is some function of irrigation, density, and fertilizer. I'm also including those asterisks in there, which means that I'm going to allow for all the possible interactions. So the three-way interaction between irrigation, density, and fertilizer, as well as all the different two-way interactions. So density by, or irrigation by density, irrigation by fertilizer, and density by fertilizer. And then the reason why I'm calling this my super fat model is that I'm also just going to go crazy here with the error structure, where I'm going to allow each field to have a different slope for fertilizer, a different slope for density, and a different slope for irrigation. And so I can go ahead and I will run my super fat model. Let's run that. Here's my super fat model. And again, what you see here is we get this singular fit warning. And we also get all these other warnings that we always get whenever I have an extra monitor hooked up to my computer for some reason. But here again, it's saying we might have a problem. There's a singular fit, meaning that the internal workings of the computer could not come up with an independent solution for all of those different slopes and the intercept in the error term. And so what we could do then is we could again use our friend the step function to help us do a little bit of model selection. So I'm going to say step super fat mod. And I'm going to do that, and I'm going to get all these warnings as it's going through there saying it's not happy. And so what do I end up with? All right. And so in the end, what I end up with is an error structure that each field will get its own intercept and will also allow the slopes among those fields to vary as a function of irrigation. Now remember when we did the simpler model, where irrigation was the only predictor in the model, that was considered too fat of a model. It couldn't independently estimate those parameters. However, after we've added in irrigation, density, and fertilizer, now we have a situation where we can uniquely estimate the effective irrigation across those fields. So we're going to end up now, what the step function is telling us is that the best model that we have is one that has both a random slope and a random intercept and a random slope for irrigation. So let's go back and see what the step function did. The first thing that the step function did was it figured out what the random effects were in the model. So again, this is the suggested approach to dealing with mixed models, is first figure out your error structure. After you've got your error structure figured out, then go ahead and figure out what your what fixed effects should be in your model. And so again, what we've ended up with here is a model where irrigation, density, and fertilizer are all in the model. We're going to allow each field to have its own intercept, and we're going to allow the slopes to vary as a function of what field that they're, as a function of whether or not you're irrigated across fields. And then it's also saying that we should have these different interaction terms in there, that we also want an irrigation by density interaction and an irrigation by fertilizer interaction. So we would have gotten the same answer had we just done it as kind of two separate approaches. So as I mentioned, the accepted approach is to first do your error structure and then do your fixed effects. So I'm going to do just the error term. So I'm going to create an object here where it's going to be called error superfat model. And why are people bothering me? Go away. All of you. Okay. So I'm going to have a superfat model just for the error structure, where I'm going to allow fertilizer to have a different slope for each field, and each field to have a different slope for the effective density, and for each field to have a different slope for the effect of irrigation. And I can go ahead and I can run that, and again, it's going to give me this warning message. Hey, it looks like you got what we might want to call a singular fit. And let's go ahead and look at that model. And again, here's all of those correlations, right? They're perfectly correlated with one another. And again, that's telling us that the computer was unable to come up with a unique solution. So if I were to use the step function on my error superfat model, get all the warnings, and then after the warnings get out of the way, what do we end up with at the very end? We end up with the best model being one that allows each field to have its own intercept and slope as a function of irrigation. That's the same thing we did when we stuck the superfat model into the step function. And so but since we're proving to ourselves that this is how it's working, now we have our best model for just the error structure, which again includes irrigation by field. And so now we could explore the fixed effects. And so I've done that here, where I'm sticking with what I believe is the best error structure, and then I'm going to explore all these different predictors, including the three-way interactions and all the two-way interactions. And we go ahead and we do that, and then I can say step, my fixed superfat model, oops, do that again, okay. And it goes through, and now we're just dealing with the fixed effects, and we end up with the exact same model that we ended up with when we just threw the superfat model into that step function. So again, it's telling us that we want all the predictors to be in there. We also want the interaction between irrigation and density, and we want the interaction between irrigation and fertilizer. And our error structure is going to be one where each field is going to have its own intercept and slope associated with the effect of irrigation. And so this then will be our final fat model. And so I can go ahead and I'll just cut and paste this. And I'm going to call this the final mod, which is going to be an Elmer, where that's what I cut and pasted in there. Make this look a little prettier. Pretty. There we go. And what is the data called? Data equals yields. Okay, notice we did not get a warning. We got no singularity problems. We have our final model. We have parameter estimates from our final model. So we could do the same trick that we did when we played around with factorial type designs before. We could look at the dummy coding that's involved with that, and we should be able to come up with a predicted value for each of those. And then finally, we could go ahead and we could do the ANOVA on our final mod. Looks like that. Okay. There's the hypothesis testing part. And then just as we did before, when we notice that there's this significant interaction term, what that's telling us is that we can no longer trust the hypothesis testing for the fixed effects alone. And so what we'd want to do is a follow-up, and we would want to split those into separate models. So we would run this exact same procedure then, only looking at high irrigation or only looking at control irrigation, to understand what the effects are on density and fertilizer. And of course, you know, we used the Elmer test version of ANOVA here. We could also have used ANOVA, capital ANOVA from the CAR package, which will do that modification of the likelihood ratio test. And there it is right there. Again, it's telling us that these significant interaction terms are there. And if we were really, really motivated, we could have done it as a bunch of likelihood ratio tests, because what I could do is I could say, I could have my final mod with, let's say, no irrigation by fertilizer. And so I could go ahead and I could drop that one little interaction out right there. And now if I were to use the lowercase ANOVA function and given it two models, it will know that we want to do a likelihood ratio test. And what's that telling us? It's telling us that the full model, the one that includes the interaction term, is significant. So that's its way of telling us that it's a significant interaction term. Obviously, doing it as a bunch of likelihood ratio tests can become very cumbersome, because then you'd have to do it for all possible combinations of models to find out what the best model is, which is why that capital ANOVA function is nice. Final fat mod, because it's basically doing that for us behind the scenes so that we don't have to deal with all those typings. And then again, we could do it in the more traditional one. Is that. And, you know, again, we have our associated p-values for our hypothesis testing. And so again, what we would do then at this point, I'm not going to do it now, but because we've done it before, but now we'd want to separate the model into two separate models to understand what's driving that interaction term. Our parameters are fine. The hypothesis testing is the part that is suspect. Okay, so now what we've done up to this point is we've learned how to set up our error structure, and we've learned how to partition our error structure both by allowing different intercepts across each of our experimental blocks. In this case, the experimental block is field, and we've also explored models where we've allowed the slope to vary across those fields. And so that is the initial introduction to mixed models. What we'll do following this is think about different ways in which we can use mixed models. And again, it's going to be an example of where things will have a different name, but it's really the different names, such as nested designs or repeated measure designs, where that's really all about the experimental design. The analyses are going to be entirely consistent with what we've been doing right here by putting some structure to our error. So on that, have a good one, and I will talk to you soon.